So my name is Erik Osheim. I work at a company out in Boulder called Precog with some other people who you all probably know or are friends with. I don't know. Scala's one big happy community, so we sort of all know each other, I feel. Anyway, my talk is kind of on a weird topic. It's something that you're not really supposed to do, and it's kind of frowned on, and a lot of my coworkers probably would disagree with a lot of stuff in my talks, so we'll sort of see what you think. I mean, it's not a troll, but it's like a quasi-troll, so don't, just accept it in the spirit in which it's given. Anyway, so it's basically about low-level optimization, and this is what you don't want to do, but this is what people sort of think you're doing. So anyway, let's get started. The talk is informed by a bunch of experiences that I've had writing Scala. So for 2 years, I worked at Xavier working on a GIS piece of GIS software called GeoTrellis that's intended to do very fast raster processing. So lots of data, parallel, distributed, that kind of thing. I've also worked with Tom, who presented earlier, on Spire, which is intended to do very fast, like math, algebra, stuff like that, sorting. And I've also written my own sort of collections that are intended to be faster than Scala's, and I make things fast at Precog too. So that's sort of my thing these days. But performance is fiddly, and your experiences might vary, and I'm definitely not trying to put myself as some sort of expert. I mean, there's way smarter people like Cliff Click or John Rose or people, so this is just what I found through sort of experimental testing and working on it. And I'm primarily talking about low-level optimization. So the idea here is that we want to basically produce bytecode that the JVM will run faster. I mean, it seems easy when you put it that way, but there's actually lots of things I could be talking about. So first of all, it is hotspot specific. If you're running one of the other JVMs, hopefully some of it applies, but I can't speak to that. And I'm focusing on code that you write in Scala. I'm not talking about you writing Java or C or anything like that. And I do profiling. I think profiling is important. I think everyone should do it. I'm using Caliper and JProfiler, but other stuff is great. The things that you could do that I'm not going to talk about are buying bigger machines, get a better JVM that's just smarter. And you can do a lot of tuning at runtime just by tuning parameters, like which garbage collector you use. I'm not speaking on that. That stuff's really important. It's just not the focus of my talk. You can also call out to native libraries. People doing linear algebra do this all the time. And of course, you can use parallelism to just run a whole bunch more processors. I'm really talking about kind of classical, single-threaded stuff. Not that these are bad, but even without these, we can still do a lot. Great, and so how many of you feel like you know a lot about how HotSpot works? I mean, I'm sure a bunch of you do, but great, so a few of you do, a few hands, awesome. So HotSpot is a just-in-time compiler. When the JVM is running your code, initially it's interpreting it and it's pretty slow, and then when you run it a bunch, it sort of warms up, and HotSpot actually compiles a more efficient assembly version of your code, and we'll do a bunch of optimizations at runtime. And this is really nice, as opposed to, say, C++, where if the GCC gets it wrong, it's wrong forever, right? And no matter what you do, it's going to, you have to recompile. The JVM is kind of great in that it will make our code faster. So a bunch of the things, these are some of the main things that it will make your code faster, is inlining small methods to avoid method call overhead, eliminating range checks, so when you're looping through a big array, it doesn't have to check every single time to see if it's out of bounds or not. And then really optimizing virtual method calls. There's lots of other stuff it does, but I think these are kind of the big ones. Those are the ones that I think is worth checking out. And you can see a full list of all the stuff it does. And then here are I'm just going to really quickly give you like a bird's eye overview of all the things that can go wrong with this. So megamorphic dispatch is when you have a whole bunch of classes implementing one interface. At that point, you can no longer inline any particular implementation. It has to use a virtual method table, which turns out to be a lot slower than, like if you call a method on a final class, the JVM knows which class you're talking about, and it can just essentially almost use like a pointer to go right there. If you have an interface and there's 10 classes and it doesn't know which one, it has to jump through a whole table, which is a lot more expensive. If you have small methods that you'd like to be inlined, but they're a little too big above this arbitrary 35-byte limit, they won't be inlined, and that can be a disaster for people. There's also how you write your loops or how you write your code. We often have to do error checking or handle edge cases, but if you do that at the same point where you're also just doing a lot of work, you'll slow the whole thing down. HotSpot won't be able to deal with that. That also kind of covers complicated loop tests. And people, sometimes when they hear about inlining, they go inlining crazy and start inlining everything, and that's actually a disaster too, because at that point, HotSpot will have other problems in terms of like the code cache, you have too much code, and when the code cache fills up, that's the last point, that's a complete disaster. At that point, your application will stop compiling anything to assembly, and it'll just sit there and be incredibly slow. And you'll see a little message in your logs, and you'll wonder what the hell it means, and you'll Google it, and you'll find out that it's a disaster. So as you can see, it's actually very important that we get this right. And so the question then is, like, how does Scala interact with HotSpot normally? And the answer is pretty well for the most part. I mean, we're encouraged to write lots of small methods. As I said, HotSpot is great about inlining those. Composition, HotSpot also deals pretty well with that, actually, because of inlining. So having to jump through 3 objects to get to something, if HotSpot knows that's what it's doing, it can inline that pretty well. And immutability is nice because it means that you have to do a lot less defensive coding, defensive checks, and those kinds of checks inside of your loops will interfere with HotSpot doing its thing. But there are problems, and the biggest problem really is garbage. Scala is a huge litter bug, and it's just allocating tons of stuff all the time, and the JVM tries to keep up, but sometimes it doesn't. Most of the time maybe it does. And I would say idiomatic Scala actually tends to produce more garbage, so that's a thing. And then there's sort of ugly side issues, like there's a lot of class files, there's a lot of bytecode, and this sort of inlining problem in terms of not being able to inline megamorphic dispatch. Scala, like anytime you call map on an array or a list or whatever, you're probably hitting the megamorphic inlining problem because you have 4 different times you call map on a list, you use 4 different functions. It can't inline that function apply because there's 4 different versions, and so it has to do a virtual method dispatch on your function object to see whether you're multiplying by 2 or dividing by 4, whatever it is that you're doing this time. And that's what gets talked about as the inlining problem, and that will hurt you a little bit. So then there's the big one, though, I said, is garbage. And so I'm just going to go through all the different ways that Scala produces garbage. So boxing, do you all know what boxing is? It looks like everyone does. Great. So does anyone want to guess how many Java lang integer instances this code snippet is going to create? How'd you get 36? No, the answer I think is, someone might be wrong. I think the answer is 16. I think it's 3 times 5 plus 1. You're going to box all 5 values in the vector. When you do the map, you're going to create 5 more boxed values that have been multiplied. And when you do your foldLeft, you're going to box the 0 first, and then you're going to box all the 5 values as you accumulate. So that's 6. And in general, what this means is that this code, if the vector was n things long, you'd have 3n plus 1 boxes you're allocating, right? And this isn't so bad when you have 5, but if you have like 500,000 or something, you can imagine where you could have a problem. No, I'll get to that. You should not, except for function 1, function 2, and function 0, and a few other things, nothing is specialized. So I think there's this assumption that Scala has specialized a lot and is really smart about this, and I think that was always the hope, but it is not true right now. So in here, you can also just this isn't boxing, but cons cells are objects, they're allocated. Every time you call these collection API methods, you're allocating a whole new list, and so, as you burn through this list, you're gonna, allocate a bunch of stuff, in addition to all the boxing that you're also doing, right? So you're gonna get a lot of allocations this way. And then the other one is using short-lived immutable objects, right? So in this case, we're computing the max and min at the same time. We're being smart, right? We're only doing 1 pass over an array. So we're computing both the min and the max at the same time, which is great, but we're allocating a tuple for every single loop iteration, right? So again, this is fine, but when your array gets really big, there's just going to be a lot of garbage. And you get a similar sort of effect when you use option, right? If you use collect or something like that, all of these types of things there's just going to be a per iteration garbage that we're talking about. Another example are biname parameters and function references. I think these are less of a problem often, but the one that really bugs me is Scala-Z semigroup append, because you tend to use that for adding numbers and stuff, and so you think it's going to be fast, and it actually allocates a function instance for every single addition that you're doing through the append method, right? So Spire's append is strict and not lazy, precisely because we're optimizing for the case where you're doing it 1,000,000 times. And then the last one, which is less of a big deal now, but using implicits to add methods to stuff. If you're not careful and you do that in a tight loop, again, you're going to be instantiating 1,000,000 of these implicit objects. So what's the conclusion, right? Do we have to write Java? But I say no. That's definitely not my position. I feel like when you see all the boxing happening, that's kind of your first impulse. You're like, oh no, all this beautiful stuff means that my stuff has to be slow. But the answer is no. Your code doesn't have to be slow, and you can still write Scala. And the thing to note is that we actually do fine most of the time, right? I mean, I just showed you all this horrible boxing, but yet you guys are all writing code that's probably pretty fast. It's getting the job done. It's not really a big deal. You know, the JVM has a really good garbage collector, and it expects to be dealing with lots of garbage. So actually, you know, often it's not such a big deal. And more than that, allocating a few objects here and there, it really doesn't matter at all. I mean, even if it's kind of inefficient, if you only do it a few times, it has to be really inefficient before your end user will notice that. So the real problem here is when you are having like order n or worse, like n squared or something, allocations, and your n gets really big. That's really the only case you should be worrying about for allocations. And so that tends to be like in a tight loop over a big array, over a big data set, over a huge table, stuff like that. That's the place where I feel like you suddenly have to have this different mindset where you're trying to like have an eagle eye for this kinds of stuff. In those cases, you want the ratio of actual work you do to be relatively high compared to the sort of random allocations that you're performing. I mean, it's fine to do some of them, but if you're spending more time instantiating tuples than adding numbers, you know, you have a problem, right? I mean, it's just not a good plan. And I feel like we all often have a good intuition about this. Not always, but we often know where the critical path is. I mean, and when you don't, it's pretty easy to find out. I mean, JProfiler makes it easy, and so while we're talking about this, I just want to address this premature optimization thing, which I sort of use tongue-in-cheek, but it's a real concern. And you know, Donald Knuth cautions us that we should forget about small efficiencies, say about 97% of the time, and that premature optimization is the root of all evil. And I think this is true, but to put it in context, Knuth also says, in established engineering disciplines, a 12% improvement easily obtained is never considered marginal. And I believe the same viewpoint should prevail in software engineering. So I think people remember the first part, but not this part, which is that Knuth is really talking about, you know, people fiddling assembly stuff to try and eke out a 2% gain or something. He's not, if your code's going to be 4 times faster, like I think Donald Knuth is totally fine with you optimizing for that case, you know, and I just like to imagine he is at least, I mean. And so most of the stuff I'm talking about, I tend to think 2%, it's 2 times for me. If something isn't 2 times faster, it's maybe not worth doing. That tends to be my cutoff. And I like to think of orders of magnitude in terms of base 2, not base 10, because a base 10 jump is really huge, and you often can't get that. Whereas if you get 2 times or 4 times or 8 times speed up, those are significant, and I think it's like I tend to like thinking of that as multiple orders of magnitude. I mean, it's an opinion thing. Anyway, this is a giant slide. And here are my giant list of premature optimization tips, which is sort of what I've been talking about. The big thing that you might be surprised about if you have never talked to me about this stuff is that I really think you should use arrays in tight loops. I really think the array data type is maligned and it gets a bad rap because of Java, but it is pound for pound a really great compact representation for lots of data, and you can iterate through it really fast. The HotSpot has lots of ways of making array access fast. It has array bounds checking. It can elide that. Arrays tend to have good cache characteristics. So that's maybe one thing you'd be surprised about. Also, when you're in the critical path and your code is too slow and you need to make it faster, I would stay away from linking a bunch of collection API methods together. That's just me, but you tend to be doing lots of extra work in those cases. Like if you do multiple maps or a map and a filter and a map or something, you could have written your own recursive function that just does that all at once, right? And you would basically lose all the intermediate allocations that are going on. So I tend to think that that's better in these types of cases. And you will do a lot less allocation. Other than that, the other things that are maybe weird are, I think local vars are fine. I really don't think anyone should be using vars inside of a field that's going to be shared in like a long-lived class. But if you're in a method, I think having local vars in that method to store stuff is often the fastest thing you can do. And tailrec is actually a great alternative to that, which is you can write these nice tail recursive methods that compile to something that's actually slightly faster than a while loop. And again, you don't have to box. You can be passing as much state. You can pass 2 things or 3 things or 4 things or 8 things through without using a tuple and a fold. And your code is still functional and nice, but it's also very fast. So prefer local variables, avoid field access, avoid mutable fields, and pay attention to which classes are specialized. And the answer is very few of them are. So be pessimistic about that. And and this is sort of a follow-up on this, which is I don't hate functional programming, and I think functional programming actually kind of informs this style in a weird way, but the admission for me is that when you need your code to be faster, you just have to do what has to be done. And you don't always like it, but it's just something you need to do. So the more shared your data is, or the more long-lived it is, the more I think it really has to be immutable, and you really need to be able to reason about it in a good way, which immutable data lets you do. But with transient data, like during a fold, not before and after the fold, but during the fold, that data is transient. It's only being created for your work. It's going to be thrown away and garbage collected as soon as you're done. With transient data, I actually think I think using mutable data for that is fine. If it's going to make your algorithm more efficient and faster and things like that, or make it even just easier to reason about, to me that's really not a big deal. Some people obviously would disagree, but this is my talk, so I get to sort of make the rules. And just another point here is that if you're using local vars in a method, that method is using mutation, but it can still be referentially transparent. There's nothing preventing you from using referential transparency in a sort of big sense, but have particular areas where you need to burn through an array, or you need to do complicated resampling, or you're going to, something like that, where you kind of need to be able to have random access to an array that's mutable. And that can be fine. It really, for me, it's about minimizing side effects and crosstalk, and those are the things that are really bad. So anyway, let's go into some case studies, just because I'm saying all this stuff, but maybe I'm just lying and making it up. So here's an example where we have a list of integers, right? And let's say that we need a list, right? We need it. Maybe we're doing like a last in, first out queue or something, or we need the con structure. We're not just going to use an array, because I would love to use an array here, but let's say I can't. So here's an example where I have my list, and I'm taking the min and the max over it, and I'm using a tuple to do that. I think, I think I made a mistake on this slide. I think this actually is an array, but either way, I'm folding over something, and I'm computing the min and the max. And so the question is, how can we do better? Oh crap, this totally doesn't fit. So here's the signature of the method that I'm going to write. This isn't even actually the code. This is just the signature, and it's completely ugly and terrible. Spec is an alias for specialized because it's even longer. It just wouldn't fit on the slide otherwise. I do that in all my code because I just can't bear to type it out. But as you can see, we're taking in an array. We're taking in B and C, which are like the starting values for our fold. And we're taking in F1, which gives you given a B and an A, gives you the next B. And C and A gives you the next C. And we're going to return a tuple of B and C, right? And so this is essentially what this code here is doing, right? It's doing a fold. We're getting out a tuple with the max and the min. Great. And so then this is the body of that code. I just split it up because it's just completely unreadable otherwise on this slide. And as you can see, we're initializing our state. We've got a little while loop. It's very imperative looking, and then we're in our var, and then we're reassigning to our var based on the function, and then we're allocating one tuple at the end. So the crucial thing here is that we're not allocating tuples every step. We're maintaining state this way, and then we're allocating tuples at the end. It looks moderately horrible. Is it worth it? And the answer is yes. These are logarithmic scale, so if you see a fixed difference between those, that's actually the graphs going off, just like a multiplier effect. But I just wanted to make it visible. So it's 100 to 330 times faster. And admittedly, for small n, this isn't such a big deal because it's the difference between 25 nanoseconds and 2.4 microseconds, right? And who cares about microseconds and nanoseconds? But for 100,000. It's the difference between 4.7 microseconds and 1.5 milliseconds. And milliseconds, your users actually care about that, right? You only got probably about 10 or 20 or 50 of those to work with before people start actually noticing that your computer's doing something other than being completely responsive. So even in this dumb, simple case, you can see that it makes a difference. I mean, it seems crazy that it makes a difference, but it does. And so then there's this question of well, what's this specialized thing? How many of you have heard of specialized or kind of know what specialized is or feel comfortable using it? I guess I sort of increased difficulty there. So a lot of you have heard of it. Fewer of you are comfortable using it. I think that is consistent with my sort of survey of the field. It's basically an incredibly subtle, difficult, but necessary tool, and I've done a lot of work with it, and it's sort of my tragic flaw that I'm stuck using it, and it fails me periodically, and it's always disappointing. But at the same time, it's good enough that I put up with it because I just have no alternative. It's just so great. It is really good. And so here's sort of a quick example that taken from another talk Tom and I did to sort of show you how specialization works, if you haven't worked with it or if you don't really have a good intuition. So this is some code. It's generic. There's a type class instance of ring that we use, we call a plus method on it. It's pretty simple. We're just summing a list of A's. You know, nothing fancy. And A is generic. It could be integers. It could be anything that has a ring that can be summed, you know, from Tom's talk. So then after specialization, this is the monstrosity that we get instead. So we have all these crazy $signs. And what that basically is saying is, this is a specialized version of this method. It's not the same method that you wrote. It's a copy that has been heavily modified by the Scala compiler. And so what happened is all the A's got turned into ints. So it's definitely, you know, committed to using ints here. And not just that, but whenever it works with any methods it calls on ring, it makes sure to call the int version because ring is also specialized. So as you can see, we're instantiating a specialized rings ops thing down here, right here. And we're calling a specialized plus method. And the upshot of that is that normally with generics, you would be boxing on the way into that method. But here we're not, because the specialized version has int in the signature. And so Scala compiler uses the primitive int for it. That's basically, or go ahead. It would rarely or never be a virtual call. I mean, I'm not going to say never, but I would not expect it to be a virtual call, right? I would expect it to be essentially invoke static, which is going to be a lot better, as you say. So this is what specialization, this is the specialization mechanism. This is really just what it does. It's essentially like C++ templates a little bit. It's a little bit more complicated than templates, and in some ways I'd rather have templates at this point, but it still works. And it's still great, and it can still make your code fast. But unfortunately, there are a lot of gotchas. So these, I can't go into all of these and like why they're there, but this is like a list of things that I think you have to kind of consider when you're trying to write your own specialized code. If you're using someone else's specialized code, you can assume that they've thought about this and it's probably fine. But basically, it kind of breaks inheritance a little bit. So you need to inherit from traits, not classes. If you have a specialized class and then you inherit from it, you won't actually inherit from the specialized version. You'll inherit from the generic version, which defeats the purpose. And you get duplicated fields, and this is really one of the worst ones. So if you have a thing that has 6 fields and you specialize it, you're actually going to have 12 fields in your specialized version. You're going to have the 6 generic ones that are still there, which it inherits, and you're going to have 6 specialized ones with different types that are the actual ones you use. These other ones are just vestigial, like the hip bones of a whale, and just sit there doing nothing except for eating up your valuable memory. So that sort of sucks. The other thing you have to do is if you're using specialization, you have to be sure that you use it all the way through. Because if at any point you have code that's not specialized, it like forgets the type information. And then when you call into stuff that is specialized, it'll call into the generic version because it no longer knows which version you're talking about, whether you're talking about ints or doubles or things. Also, there's this problem down here, which is that any ref, if you mix like an int and a string, even if you're specialized, it won't use the int version because string is not, you can't specialize on string, it's an any ref type. If people want to talk about that later, I can explain it more. It's a little complicated. But basically, the advice I have for you is if you're trying to use this, keep it very simple. Don't do anything fancy. I would say even avoid fields if you can. Like the best case scenario, you're writing type classes, you're specializing those, it'll just work. It's great. If you're just specializing methods and you're taking things in as parameters and returning them as values, specialization works really well. The moment you have like constructor stuff going on and fields and different crap like that, and then there are bugs and it doesn't work and it's not specialized, and you're going to be chatting with Vlad, Ureki, and people like that. And that's probably not how you want to spend your weekend. And then the last thing I would say is if you're really invested in this, you're going to have to invest in some time running Java P and just seeing what happens. I wanted to put it in the slide. It's just too complicated. There's no way for me to actually communicate it at all about it. So like I said, very simple stuff. Basis is a cool library. He only specializes traits. All of his implementations are concrete that extend the trait. So he's doing what I said. He's only using it for methods. He's not specializing fields. He's not doing anything tricky. And I get the sense that it works well for him. I haven't really played with this library too much, but like I said, when you write specialized code, it will often end up ugly. That's just okay. I mean, there's just no way around it. So, but here's an example that does use lists, unlike the last one, which I put it in erroneously. So, in this case, how well can we do when we need a cons-like structure? So you're going to have a bunch of allocations. So then here's the sort of naive example. We have a list. We want to basically build a list of triples. Someone's going to be giving us triples, and we need to be building them into some sort of like queue. This is the example I thought I was talking about last time. Anyway, as you can see in this little code snippet, I've got some arrays of numbers, and I'm building them into a queue. I mean, this is just for benchmarking, so you can just see how fast it is and what it does. I think it's pretty straightforward what's going on here. But so then one thing you can do easily to reduce this is tuple 3 I use tuple 3 specifically because it's not specialized. Tuple 2 is. You will not have this problem with tuple 2, but with tuple 3 is not. So you'll get 3 boxes for every single one of those tuples. An easy way to defeat this is if you know you're dealing with ints, you just build your own little case class. You know, product, I think, is specialized. But regardless, the case class itself, your accessors will be typed correctly, even if the product stuff isn't. So in this case, we're only allocating one thing, and we're not boxing those ints, instead of allocating one thing and then allocating 3 boxes inside of it. Otherwise, the code is very similar. And then there's this natural question, which is like, well, can we even do better than this? And it turns out that the answer is that you can, right? So this is a little uglier, but basically, the observation here is that why allocate a tuple structure and a const structure when you can make a tuple const structure that does both, right? So in this case, we have an A, a B, a C, and a tail. We've got this weird I cons down here that basically allocates your cons structure but has enough room to put all 3 of the values in it, right? So now instead of allocating 2 things, we're only allocating 1. And this is just sort of, it's based on a very simplified version of Scala's list. You'd probably want to add a bunch more methods and stuff, which I didn't bother doing. Okay.
Microphone. How well is HotSpot's inlining and escape analysis going to be able to catch the III boxing case? I mean, obviously, when you're passing over a function boundary, it has to put it to box it to be able to pass it as a parameter. But in other cases, I mean, if you're just living within a tight loop, is that going to be okay, or do we still have to do III list?
Well, the answer is, I mean, you're still going to have to allocate those things for sure. Like, it might stack allocate them in some cases. Like, escape analysis it's never going to like remove those allocations entirely. But it will. But you're totally right. Your observation is a good one that it will often be able to reason about it a little bit better because it's all right there. So I think it can stack allocate in a lot of cases. Anyway, then there's this question which is, can we do even better than this? And then the answer is kind of. So if you are willing to make some compromises, you can basically say, okay, well, if we can go 2 at a time instead of 1 at a time, we can build this weird mutant cons thing that has 6 fields, right? And like, this might be better. It's going to have half as many things in it, so it's fewer allocations. But maybe it's a disaster. I don't know. Let's see. So the downside with that, like with vector, is that cons and uncons will be slower because you're going to have to potentially break apart these things and reconstitute them, but you'll have better memory usage, which might be worth it for you. I mean, objects, I think they have like 24 bits of overhead. Is that right? Or 32 bits of overhead? It's like something like that. It's if you're storing a 32-bit integer, that's like a lot of overhead for each one. So anyway, here's the graph. Again, this is logarithmic. So if you see these things separated, that means that there is like a significant multiplier there. It's not just like a constant shift. So what you see is that it's actually really significant. I mean, if you go up to the large amounts, I mean, that's like more than a 10 times difference. To give you context, at that top point, the yellow at the very top is 22 times slower than the green at the bottom. So that's 22 right there. So if half that distance would be like 11 times, and then half that would be about 5 times. Oh, damn it. All right. So anyway, here's sort of the results in a form that's a little easier to digest, which is that for the 100,000 case, your list of triples takes 27 milliseconds, 27.5 milliseconds. Just using III is 3 times faster already. Bam. That's super easy. It's like kind of a no-brainer. III list is ugly, but it is 9.3 times faster. So that's also pretty significant. I mean, if this is something that is critical to your business, if it's like a thing that you do once in a while, who cares? And then I6 list is weird in that if you go back to the graph, it starts out being worse here. It's the weird purple star thing, but then it kind of gets better than the one it's really near. And what's happening there is that if you have to build it element by element, it's actually worse in a way for small amounts because you're constantly swapping out the head of the list for like the 1 version and the 2 version, then back to the 1 version, then the 2 version. But when you get really large, the memory savings actually starts to take effect, which is that it's able to garbage collect instances as it's going faster. There's less memory pressure, so it actually does do a little bit better. And then the faster version, the green version that's cheating, that's going by 2. So that's the version where you're only ever creating the cons, and you're just doing that. And if you can proceed by 2, then obviously it's better to do that. And that's 22 times faster. Daniel?
Yes. So there's another alternative here that I'm curious if you benchmarked, which is going by chunks. So rather than having a list of triple of int, having a list of triple of array int, array int, array int, and then having some particular chunk boundary, which doesn't even need to be that large.
You're totally right. I mean, I didn't do that because I just knew that was going to be super fast. I mean, as soon as you put array in the picture, you're basically like list. The only time lists can ever compete with array is when you're doing like a last in first out queue that isn't ever going to get very big. And those are the cases where it wins. It just loses across the board. So if I let array, I just didn't even want array. It's like heavyweight and welterweight boxing. You know what I mean? It's just not even. But you're right. I mean, you're totally right that that's actually a great model. And that's sort of what's being gestured at. So sort of tying into this, I mean, cheating is good. If we can proceed by 2 instead of by 1 and it's better, we should do it. You know, we should take advantage of whatever we have. You know, we shouldn't force ourselves to stick with the most generic solution if there's a way that we can cut a corner and be a lot faster. And I like type classes, you know, because they give you that flexibility. The ad hoc polymorphism means that if you end up with a certain type and you know you can do something really sneaky, you do it, you know, and that's great. It's a way to be functional and to do that. And I need to proceed because I'm totally behind. Anyway, boxing and allocations aren't always the only thing. I sort of have made it seem like they are, but they aren't. And so cache coherence is also really important. And I have an example that kind of shows this off. So here's 3 different collections of 2-dimensional points, right? The top one is a naive array of points. The middle one avoids allocating point objects and has an array of x coordinates and an array of y's. And the bottom one interleaves. Actually, the bottom one is the wrong code example. Crap. It's supposed to be one array of x, y's. That's what I benchmarked. I just copy-paste error. Anyway, it's going to have one array where the x and y coordinates are interleaved, if you can imagine that, right? And the scaling operation I'm doing is I'm basically I'm taking the distance from the origin, and then I'm scaling the x and y coordinates by that. So I'm basically mapping the points into the unit circle somewhere along there. It's a pretty dumb little thing, but you know, it's enough work that it's actually significant. I didn't want to do something super trivial. So I'm not going to show you the other instances. They're not interesting. The one thing to remember is that the array is twice as long for interleaved points, and that it's going to step by 2, not by 1, because it's going x, y, x, y. And as you can see here, the interleaved points is 3 to 6 times faster, but the other 2 are basically the same. So the array of points and the 2 arrays of x's and y's are basically identical until you get to a certain point where the array of points falls off a cliff, basically. And what you can see there is that JVM is actually really good at doing garbage collection of very short-lived objects, but at a certain point, what's happening is, or it's very good at allocating a lot of objects and dealing with like massive allocation requirements, but at a certain point, it becomes too much, and you actually start hitting a wall a little bit. And so they're the same up until the last point, but for the very last one, the array of points is 14 times slower. So you really do just kind of fall off a cliff there. And that's the thing, is if you never hit that, if you're never going to get that big, don't bother doing anything fancy, but if you are, then it's important. And the lesson here really is that the cache usage is what was significant, not the boxing or not the allocation. Anyway, this is kind of the closing remarks section. I guess I'm kind of going over a little bit. 2 minutes, great. But people would say, well, arrays are mutable, isn't that bad? And it's like, well, yes, it is kind of bad, but you know, we sort of go to war with the army we have. And I like to consider arrays as mutable only during a construction period. So I like to think of arrays as like they're mutable when you're building them, but once they're built, you shouldn't mess with them. And at that point, you should sort of treat them like an immutable data structure, and if you need to, make a copy. And making copies of arrays is actually super fast, so that's actually not a big problem. If you're someone who's a real hardliner, like you know, one of the Scala Z faction, you might want to just make a wrapper so you can guarantee your array is not going to be modified, right? You make an immutable wrapper, and then you only expose apply. That works fine. So for an example of how I kind of think arrays should be done in Scala, I would point you to this GeoTrellis project, which is one of the things I've worked on. Basically, it's all about arrays. We have these giant grids of numbers. We need to smash them together and we tile them and do them in a distributed way, and then resampling and all sorts of different junk. But at a high level, it's all purely functional. It's all referentially transparent at a high level. There isn't a whole lot of shared mutable state, and it does make copies, but at the same time, at a low level, it's able to be very fast because it doesn't try to enforce that immutability down to the cell level. It only enforces it down to the chunk or the raster level, at which point those can have very fast implementations in terms of, you know, tail recursive stuff or while loops or whatever. And even in that case, at a high level, you can still call map on a raster, and it will still do it like really fast. We just have some tricks to sort of smooth stuff out, and rasters aren't generic. They're specified to be either int or double or something like that. So there's a lot of interesting stuff you could get there if you're interested in this kind of thing. What about vector? I don't know. For the kinds of stuff I'm talking about, I really don't think vectors are that great. I think for mid to high level code or shared code, they're really good, but amortized, effectively constant time access is not array access, and it's just a lot slower. So also they box. They're not specialized, like I said. So, you know, you're going to have those issues. These are really the only, I think in 210, these are the only specialized types, basically. So if it's not one of these on this list, you should just assume that it's going to box all the time. Arrays are a special case. Arrays also don't box, because they're sort of like a primitive in a way. And I would encourage you to use value classes. That's another way of removing allocations. Java or Scala? Scala? This is 210. I mean, yeah, before 210, actually, I think function 2 was not specialized in 2.9. That was actually a big problem for a lot of people. So if you implemented generic binary operations, 2 inputs, 1 output, it wasn't specialized. And a lot of people would have to create their own manual function 2 to get around that, which was super annoying. And then what about the other collections? Well, I don't know. I mean, for this, again, in the sort of narrow scope of premature optimization, if you know exactly what you need to do, you can probably do something faster than the generic thing built for everyone. I mean, not always, but I would say often. I've done a lot of work in this, and when you have a specific thing in mind, if you don't need generic types, you can skip them and you'll save a lot of time. If you don't need, whatever you don't need, just don't do, and that'll be better. I sort of am advocating not invented here a little bit. You're the best judge of whether it really is worth doing or not. But if you can get a 10 times speed up, it seems like maybe it's worth a little NIH to get that. So this is kind of my ethos. Is I really strongly believe that it's important to profile your code, come up with a baseline. Because if you noticed all of my graphs, it wasn't just one thing. It was like a bunch of things to get a sense of where your solution fits in the ecosystem of what other people are doing, or what the state of the art is. Because otherwise, you just don't know. You might think your thing's fast and it's really slow, or vice versa. And pay attention to the versions of stuff you're using. Java 7's a lot better than Java 6 for a lot of things, so that's worth knowing. And finally, make sure to test correctness. I mean, I've definitely done the thing where I think I've implemented some insanely great data structure, only to find out that it's actually not working properly. So it seems so fast because it's not doing any work. That's a pretty humiliating thing, and the last thing you want to do is crow about it on Twitter or something and then find out that your thing is completely broken. So make sure to also actually test it, not just benchmark it. And then, again, this is sort of what I've been saying. I think functional programming is great. I would be reluctant to give it up. But if you can minimize the area where you need to do something unsavory, you should have no compulsions about doing an unsavory thing to achieve your goal, basically. The ends justify the means. I've said it. And then there's a bunch of awesome links. There's people who are way smarter than me about this stuff that I've learned a lot from. Here's a bunch of different interesting links that talk about various things I've either alluded to or mentioned. And if you look online, you'll find lots of stuff. So that's it.